All right, for question number 8, we're asked to find dy dx again, so we're taking the derivative. And then notice that I'm taking the natural log of, stuff. So my basic natural log rule, so I'm just taking the derivative of the natural log of x, that's equal to 1 over x. So if I'm taking the derivative of the natural log of u, where u is a function of x, then it's going to be 1 over u times u prime. It's one of those chain rules. And again, another way of writing this, a lot of people will write it as just u prime over u. That way when you take the derivative, it's already simplified. Okay, so coming over here, I'm taking the natural log of stuff. So like I said, my u is going to be 4x cubed minus x squared. So dy dx is equal to 1 over u, so 1 over 4x cubed minus x squared times the derivative of u. So the derivative of 4x cubed minus x squared. That'll give me 12x squared minus 2x. Right, and so simplifying this or rewriting it in this fraction, I get 12x squared minus 2x all over 4x cubed minus x squared. Usually you're done right here. This one happens to have an extra step. If you notice that there's an x I could factor out of the numerator, and an x I could factor the denominator. So I need to factor those out and cancel them. And then we have, taking the x out in the denominator, we get 4x squared minus x. So now I can cancel these x's, and so my final answer, reduced fraction, will be 12x minus 2 all over 4x squared minus x. And we used our general logarithm rule. Number 9. Here I'm asked to find dy dx again, and one thing that's different is notice that I've got two functions. So in this first one I've got y as a function of x. So if I take the derivative, then I get dy with respect to u. And then when I take the derivative of u, it's with respect to the variable x. Since I got x's on the right hand side. What happens if I multiply those two together? So if I take dy du and multiply it by du dx. Notice that our du's kind of cancel, and so I end up with dy dx, which is what I'm looking for. So that's our basic approach. So I'll take the derivative of y with respect to u, then the derivative of u with respect to x, and I have to multiply the results together to make it work. Okay, so coming back up here to my function y. One thing I would do is rewrite this. So y is equal to 8u to the negative 2, and now I'll take the derivative using my power rule. So I'll bring down my exponent, I get negative 16 u to the negative 3rd power. And then for my u function, I'm going to leave it alone. I don't have to do anything there. So when I take the derivative, I get just plain old 4. All right, now multiplying those together, I take my dy du, so negative 16 u to the negative 3rd, and then I have to multiply that by du dx. So multiply that by 4. And this will become, multiply my coefficients, I get negative 64 u to the negative 3rd. There's one more problem. My answer's got a u in it, and I really wanted dy dx. But remember, if you come back up here, we know what u is. U is equal to 4x minus 3, so I've got to make that substitution. So last step, dy dx is going to be equal to negative 64. Now I know what u is, 4x minus 3 to the negative 3rd power. I'd be happy with you writing your answer like that, but if it's multiple choice, you got to match it up. So we're going to have negative 64 in the numerator, and then 4x minus 3, positive 3 now in the exponent. All right, so number 10. So I'm asked to find the derivative of q with respect to the variable p, so dq dp. The other thing you'll notice on this one is I don't have an explicit function. Like normally we have f of x equals, some function of x. Here I've got my p's and q's kind of all mixed together. The other thing is if you look at the directions, I'm telling you, use implicit differentiation. On the exam, it'll be very obvious. The directions will say, use implicit differentiation to find, dq, dp, or dw, dt, whatever it is. Okay, so what I need to go is take the derivative of each term with respect to the variable p. So when the variables are the same, that's what we've been doing all along. So when I take the derivative with respect to p of 8p squared, that's what we've been doing. So that's just going to be 16p. But now when I want to take the derivative with respect to p of q squared, I've got a bit of an issue because the variables do not match. So you want to think of q as being a function of p. I'm using my general power rule here. So I'm going to bring down my exponent. We'll decrease it by 1, but then I have to multiply it by the derivative of q with respect to p. And that's how I get my dq dp. I want to take the derivative with respect to p of 1300. I just get 0. Like I said, any constant derivative is going to be 0. So I'm not quite finished now. I have to go ahead and solve this for dq dp. So I will bring the 16p over. So we have 2q dq dp is equal to negative 16p. And then I'll go ahead and divide both sides by the 2q. So those will cancel. And that will give me my result of dq dp is equal to negative 8p all over q. I also reduced my fraction, the 16 and the 2. Number 11, we are asked to find the percentage rate of change. So like I said, when you get into these applications, you've got to learn how to read the questions looking for keywords. So rate usually tells me to take the derivative, but a percentage rate of change, a relative rate of change, those are a little bit different. So I'm looking for the percentage rate of change. So remember that our formula, so I take the f prime of x over f of x and then convert that to a percent, so times 100%. So the relative rate of change, f prime over f, and then convert it to a percent. All right, so for my function here, f of x, f prime of x is going to be negative 8x. And so f prime evaluated at 20, negative 8 times, I get negative 160. That'll go in the numerator. And so f of 20, using my original function, I've got 4,500 minus 4 times 20 squared. And so let's see, that will give me, that's going to be 2,900. Okay, so my relative, or my percentage rate of change is going to be negative 160 divided by 2,900. And then I have to, like I said, convert this to a percent. So I'm going to do this part here. I get 0.05517, a bunch of stuff. Convert it first to a percent and then do your rounding. So this is equal to negative 5.517%. And then rounding to the nearest tenth. The one says round down, so negative 5.5%. That is my percentage rate of change. All right, so for number 12, let's see. We are given the price demand equation, and we are supposed to determine whether the demand is elastic, inelastic, or has unit elasticity. Okay, so a couple things I need to remember. My formula for elasticity. So E of P is equal to negative P times F prime of P over F of P. Also, if E of P is greater than 1, we say it is elastic. And if it's elastic, that means we're going to have a big change. So the demand will decrease by a lot and our revenue will decrease. If the elasticity is less than 1, then it is inelastic. And so that's going to be a small change. So we increase the price, the demand decreases, but by a smaller amount, and so our revenue will increase. And then if the elasticity happens to equal 1, then we say it has unit elasticity. And that means if the price goes up 10%, the demand is going to go down the same amount. It goes down 10%, and my revenue is the same. All right, so coming over here to our function, E of P is going to be equal to negative P times, so I need the derivative. So 2,500 I'm sorry, 205 minus p squared, so the derivative is negative 2p, and then all over 2005 minus p squared. I'm going to simplify this a little bit in the numerator. I'm just multiplying those together, so we get a positive 2p squared all over 2005 minus p squared. Okay, now I have to evaluate it. We're given that the price is 13, so we're going to plug in our 13, so 338, and then in the denominator I get 1836. Well, it's definitely less than 1, but let's see, it's 0.184. Okay, since that is less than 1, we would say it is inelastic. And again, what this means is if my price increases by, let's say, 10%, then my demand is going to decrease by 1.8%, and my revenue will increase. Okay, so I just went ahead and wrote that out for you. So again, if the price increases by 10%, the demand will decrease by 1.84%, and the revenue will increase. Remember that price and demand are inverse functions of each other, so anytime the price increases, demand will decrease. And then I found the amount it'll decrease, that 1.84%, by taking the elasticity times the percentage that the price increased. So I took my 0.184 times 10%, and that's where I got my 1.84%. Number 13, we're asked to find the equation of the tangent line. All right, so anytime I want to write the equation of a line, I'm going to start with y minus y1 is equal to the slope times x minus x1. And I've got to plug in values for, y1, m, and x1. Now, x1 is given to me. It's supposed to be when x is equal to 7. So how do I find the y value? Well, the y value is the function value at 7, so it's just going to be f of 7. So we get 6 minus 7 squared, so 6 minus 49, I get negative 43. So that's my y value. Now to find the slope of the tangent line, I need to take the derivative. So f prime of x is going to be a negative 2x. Therefore, the slope will be f prime of 7. So negative 2 times 7, my slope will be negative 14. All right, so now I plug in the values and simplify. I'm always going to ask you to write your answer in the slope-intercept form. All right, so we have a y minus negative 43, so y plus 43 is equal to my slope, negative 14 times x minus 7. So now I'm going to distribute the slope. So I have y plus 43 is equal to negative 14x plus 98. And then subtracting 43 from both sides, we will get y equals negative 14x plus 55. And this is the equation of the tangent line at x equals 7. So you can plug this into your calculator or just, rewrite it as a fraction. So I've got 10 divided by, because the negative exponent, and that'll be the cube root of 8. So 10 divided by 2 will give us 5. So I've still got to figure out what my labels are. So again, going back up to the original problem, we know that W measures the amount of learning. So W of T is going to be the learning, and it is measured in terms of what? That's the number of items. So it's the number of items. And then T is our time, and it's being measured in terms of T hours. So after T hours of instruction. So now if you take the derivative, W prime of T, you're going to get something per something. The label for the first part will be the label of W, and then the second part goes for T. So my label for this one is going to be number of items learned per hour of instruction. So items per hour. Okay, so for number 15, I'm given the area of a circular oil spill, and I know it changes with respect to the radius. At what rate does the area change with respect to the radius when r equals 10 feet? So again, I'm asking you, what's the rate? So I have my function, a of r equals pi r squared. So when I take the derivative with respect to r, I bring down my exponents, I get 2 pi r. And now I need to evaluate this at 10. So a prime of 10 will be 2 pi times 10. I get 20 pi. And so what's my label going to be? All right, so like I said, going back up here, I know that a, which measures the area, is being measured in terms of, well, area is always going to be square units, so that's going to be square feet. And then the radius is in terms of, like in this case here, a radius we're told is 10 feet. So that's my radius, and it is in terms of feet. So when I take the derivative, a prime of r, my label, something per something. So area, I get square feet, and my radius was in terms of feet. So my answer is going to be 20 pi square feet per foot. There you go. We are given a car's distance in miles from a starting point after t hours. It's given by s of t, and we're asked to find the average velocity as t changes from 5 to 7. Now, if I were asked to just find the velocity, I would take the derivative, but average velocity is a different function. So average velocity is like the average rate of change, slope of a secant line. All those are over a period of time or from the change in 2 points. So you're going to take the change in the y's over the change in the x's. Or, we often see it as f of x2 minus f of x1 all over x2 minus x1. For this particular one, my function is s of t, and I'm going from 5 to 7. So my average velocity will be given by s of 7 minus s of 5 divided by 7 minus 5. I'm going to go over here and find my function values. So for s of 7, plugging it into s of t, we get 5 times 7 squared, so 5 times 49, we get 245. And then s of 5, we get 5 times 5 squared, which is 125. Okay, so plugging it back in here to my formula, we have 245 minus 125 all over 2. And so this will give me 120 over 2, or 60. So I've got to figure out my labels, of course. So my distance is in terms of miles, and it's after t hours. So my label is going to be miles per hour. And that is my average velocity. Question number 17. An object moves along the y-axis, marked in feet, so that its position, time, in seconds is given by f of t. Find the velocity at 3 seconds. Okay, so now we're asked to find the velocity. Since it didn't specify average velocity, we know that means instantaneous velocity. The velocity is going to be equal to the derivative of the distance function. So it gives me the change with distance with respect to time. So f prime of t is equal to 27t squared minus 18t plus 1. And I want to know the time, I want to know the velocity at 3 seconds. So we use time 3. So 27 times 3 squared minus 18 times 3 plus 1, which gives me 190. So I've got to figure out what my label is going to be. So going back to our function, notice that it moved along the y-axis in feet, and that time was measured in seconds. So my label will be feet per second. So feet per second.